Today we shall continue limit state of collapse Flexure part 2. So, that is our lecture 7, limit state of collapse Flexure part 2. Last class we have started limit state of collapse Flexure singly reinforced section, that where reinforcement in the tension side, stress strain curve, the strain diagram and the corresponding stress diagram. The ultimate strain in steel, it is dependent on FOI. We shall get epsilon SU equal to 0.87 FOI, taking 1.15 as the partial safety factor for materials. So, 0.87 FOI by ES plus 0.002. We have also done the problem. If we know, I shall show you that expression of resistance moment for a balanced section in terms of FOI and P. We have derived the equations in the last class. Today we shall start expression for resistance moment in terms of concrete strength FCK. Mu equal to 0.36 FCK times X times B. This is the compressive force multiplied by D minus, let us put it 0.42 x. We can put it 0.41 x, you can also find out 0.4 x also in different books, but we shall take, let us say here 0.42 x. 0.36 FCK times x multiplied by BD times 1 minus 0.42 x by D. We can further write down 0.36 FCK x by D times 1 minus 0.42 x by D times B D square. So, here B D and another D is coming from here, x by D. So, we can get, this is one expression we can consider, or we can write down in this fashion also, 0.36 x by D multiplied by 1 minus 0.42 x by D times FCK B D square. This is one term, 0.36 x by D times 1 minus 0.42 x by D FCK B D square. For different grade of concrete, we shall get, this is dependent on this FCK. We can also write down, say, capital K FCK BD square. Further we can write down mu by BD square equal to K FCK. We shall get mu by BD square equal to K FCK. You can refer annex G of IS 456 2000. So, mu by BD square equal to K FCK, where K is nothing but 0.36 x by D 1 minus 0.42 x by D. So, let me continue. For Fe 415, xu by D, that is the limiting value that we have seen, equal to 0.48. Therefore, mu equal to 0.36 x u by D multiplied by 1 minus 0.42 x u by D times FCK BD square, which comes as 0.36 multiplied by 0.48 multiplied by 1 minus 0.42 times, let me put it this way, 0.48 FCK BD square, which results 0.138 FCK BD square. So, for concrete grade for M20, we can multiply with 20, we shall get the required strength for concrete for a particular grade section. Next, we shall come steel area. For balanced singly reinforced section. Here we shall take, we always refer, we can refer say C and T, and this is your that lever arm here, lever arm, and this is K2x, that where from the top compressive fiber that C is acting. For the balance section, we shall get that yield stress in the steel, that will be 0.87 FOI, and we have also reached the 0.0035 the strain and the corresponding that stress block. We shall write down 0.87 FOI AST, this is the tensile force, 0.87 FOI times the area of steel, that is your tensile force, which will be equal to compressive force, since it has to be in equilibrium, 0.36 FCK B times XU, that is the limiting neutral axis depth. Therefore, AST by BD we can write down as 0.36 FCK by 0.87 FOI multiplied by x u by d, or further we can write down as 0.36 by 0.87 x u by d. This is the limiting x u by d, because we are considering here we are taking balanced section, multiplied by f c k by f y. Let us say P t equal to percentage of steel in tensile zone, P t equal to A S t by B d multiplied by 100. We can write down P t will be equal to 0.36 by 0.87. Yeah, could you see? Oh my God. So, okay, let me. Okay. P t equal to 0.36 by 0.87 multiplied by 100 times x u by d f c k by f y. We can write down that percent of steel for balanced section. Therefore, we can further write down in this fashion f t k f y by f c k equal to 0.36 multiplied by 100 divided by 0.87 x u by d, or P t f y by f c k equal to 41.3 x u by d. X u by d is the limiting value, and we can get percentage of limiting steel areas for balanced section for different grades. We shall get, this is the, we can find out in the IS 456 also, x by d, and the corresponding P t f y by f c k we shall get closer to this value, depending on the number of that fractional terms you are considering, the decimal number of decimals you are considering, depending on that it may differ, or otherwise the value will come closer to this 21.97, 19.82, 18.87. We shall further go expression for x by d given b d mu. As we know, mu equal to 0.36, we can write down x by d multiplied by 1 minus 0.42 x by d times f c k b d square. already we have derived this equation mu equal to 0.36 x by d 1 minus 0.42 x by d FCK BD square. We know B, D, mu, we know and also FCK. Therefore, we can find out from this expression we can get x by d. It is a quadratic equation. In any book you can also get the closed form solution, but anyway I think that is not required. What you can do, you just put the value and get the quadratic equation and find out x by d. What about lever arm Z? What about lever arm Z? This one, the distance between C and T, that is your lever arm. I should write down here that is your lever arm. I think I can write down the equation possibly. Okay, let us see whether I can write down. So, lever arm Z, lever arm Z equal to d 1 minus we can further write down as 0.42 as you wish, 0.416 or 0.42. It is better we should continue with one value, but since we have already started 0.42, let us consider take 0.42 here. If the stress in steel is FST, which is a value less than the yield stress. We can get 0.36 FCK x by d BD equal to FST times AST. We are considering, we are taking FST is not necessarily that value, not necessarily that is yield stress FOI or 0.787 FOI. If that be the case, this still it should be in equilibrium, and from here we can get this expression. We can find out x by d equal to FST AST divided by 0.36 FCK BD. So, what we are getting then? If B and D and mu known one part, we can get from this expression mu, we can find out x by d. We can further we can get z, the lever arm, and also we can get x by d. If we know FST, AST, FCK, BD, then also we can find out x by d. So, these are the three different expressions that we can get. We can continue calculation of steel area. Given B, D mu. We can write down here for completeness FCK as well as FY. Compute x by d from the expression 0.36 x by d multiplied by 1 minus 0.42 x by d times FCK b d square. Z d 1 minus 0.42 x by d. AST mu by 0.87 Fy times Z, the lever arm. We can get mu from here, we shall get x by d, compute Z, the lever arm, then you find out area of steel. Mu is nothing but 0.87 Fy, the stress, multiplied by the area of steel will give you the force, multiplied by Z, we can get the area of steel. When you are computing x by d from this expression, mu 0.36 x by d, from this expression when you are computing x by d, then you check, let me just give a note here, you check x by d less than x u by d, that limiting x u by d for the balance section, that should be checked. It should not be more than the x u by d, that you should check from this expression. Analysis and design of RC sections. What do we mean by analysis and design? When a section is given, the section is given that width, depth, steel, the number of bars, bar diameter, then concrete grade, steel grade. When it is given, you are finding the moment capacity, then we call it analysis of RC section, moment capacity of that section. When the moment is given, concrete grade is given, steel grade is given, and also we generally assume that width of the beam, but we have to find out the depth of the beam and number of bars and the diameter, then we call it design. Analysis is everything given, you find out the moment capacity. The other way, the moment is given, you find out the depth and the steel bars to be provided. In that case, we consider that design. Number 1, what we shall do, that due to concrete failure, mu equal to k FCK b d square. Limiting values of x u by d, k equal to 0.36 x u by d 1 minus 0.42 for Fe 250, x u by d 0.53, k 0.149, Fe 415 0.48, 0.138, that is capital K, and Fe 500 XU by D 0.46 and capital K 0.133. We can get mu for AP 415, mu equal to 0.138 FCK BD square. Similarly, for AP 500 we hardly use it, 0.133 FCK BD square. If it is M20 grade of concrete, immediately we can find out the moment capacity. If it is a M25 or M30 like that, we can get the moment capacity, assuming that there is a concrete failure. Similarly, we can have the other part, that means steel failure. Let us write down from the assumption that steel reaches yield at failure. Mu equal to 0.87 FOI AST times D 1 minus AST FOI by BD FCK. You will get this expression in Annex G, IS 456 2000. We have already derived this expression mu equal to 0.87 FY times P by 100, that percentage of steel is known, 1 minus Fy by Fck times P by 100 BD square. If we know the percentage of steel, from there you can find out that mu, that also we can find out. Number 3, given mu, FCK, B and D. We have already done it. Mu equal to 0.36 FCK x by D 1 minus 0.42 x by D multiplied by B D square. Use this expression to find x by D, and x by D should not exceed the limiting value. Number 4, we are giving different cases, concrete failure, steel failure, this is another condition. Number 4, the balanced steel percentage. We write down that PT, say let us say limiting value, this is the limiting value, equal to 41.3 FCK by FOI multiplied by XU by D. This is the limiting percentage of steel for the balanced section. We can get that it should not exceed, if it is under reinforced, the percent of steel you have to provide less than this PT lim, less than this value. If it is over reinforced, then it will be more than that. The lever arm Z to D 1 minus 0.42 x by D equal to D 1 minus 0.42 FST AST divided by 0.36 FCK BD. So, we can get lever arm and then we can continue, we can find out the area of steel if it is required. We can compute the area of steel. If we know the Z, we can find out the area of steel also. Okay. Let us solve one problem then. Calculate the ultimate moment carrying capacity of a rectangular beam given B equal to 250 millimeter, D capital D 400 millimeter, steel 316 torr. We shall use this symbol to show that it is high yield strength deformed bar. Phi for mild steel, the torr, this one for high yield strength deformed bar. Concrete M20, steel Fe 415, clear cover 25 millimeter. The section looks like .316 torr, overall depth 400, overall depth 400, width 250. FCK here 20 Newton per square millimeter, Fy 415 Newton per square millimeter, ES modulus of elasticity of steel 2 into 10 to the power 5 Newton per square millimeter. Unless otherwise specified, we shall take ES equal to 2 into 10 to the power 5 Newton per square millimeter. Epsilon SU 0.87 Fy divided by ES plus 0.002 as per our code, which comes as 0.87 into 415 divided by 2 into 10 to the power 5 plus 0.002 equals 0.0038. Epsilon SU 0.0038. You can remember that one also for FU 415, 0.0038. So, shall we continue? 316 torr, we call it torr, TOR. T, we are writing TOR in this fashion. So, we call it torr. So, torr steel we can say. The other one we say phi. Whenever we say phi, 16 phi, that means it is mild steel. If we specify this symbol, then we shall assume, if the grade of steel is not given, we shall assume that is Fe415 at least. Okay. What about the neutral axis? 0.0035 concrete strain, 0.0038 steel, X and D. Therefore, X by D equal to 0.0035 divided by 0.0035 plus 0.0038, which comes as 0.479, and we know it is nothing but 0.48. X by D equal to 0.48. We can compute the balanced percentage of steel. We can compute balanced percentage of steel. Balanced percentage of steel. Let us say this is number 2. Let us write down the expression at least in one case where from we are getting 0.87 FOI equal to 0.36 FCK B times X equal to 0.36 FCK BD multiplied by X by D. We can write down 0.87 FOI P by 100 BD equal to, we are taking here percentage of steel, 0.36 FCK BD times X by D, or P FOI by FCK equal to 0.36 0.48 times 100 divided by 0.87. 0.36 BD cancelled, X by D is nothing but 0.48 times 100 divided by 0.87. For FOI equal to 415 Newton per square millimeter, that is the grade specified in this problem. FCK equal to 20 Newton per square millimeter, which we have to take in this problem. P comes as, computing all those things, equal to 0.957%. That balanced percentage of steel 0.957%. We can write down, since we have specified it as PT lim, limiting value, we can say PT lim equal to 0.957%, that balanced percentage of steel limiting value. Area of steel provided, (3) 16 torr 603 square millimeter. Percentage of steel, equal to 603 multiplied by 100 divided by 250 into what is the effective depth. So far we have not come across that. Let us find out the effective depth. Effective depth equal to 400 minus clear cover 25 minus 16 by 2 comes as 367. So, 250 is the width of the beam multiplied by 367 equal to 0.657% less than the limiting value 0.957%. Hence, the beam is under reinforced. Hence, the beam is under reinforced. We can compute mu due to steel failure. Mu equal to 0.87 Fy multiplied by P by 100, the expression we have already derived, 1 minus P by 100 times Fy by Fck times Bd square. At least once for all, let us write down the full expression. 0.657 is the percentage of steel we have computed, which is provided 316 bar. 1 minus 0.657 by 100, 415 by 20 times B is how much? 250, D is 367 equals 68987082 Newton millimeter or 68.98 kilonewton meter. Moment carrying capacity due to steel failure, we shall get 68.98 kilonewton meter. We can check what about due to concrete failure. We can check what about due to concrete failure. 5 mu due to concrete failure. Mu equal to 0.36 Fck Bd square x by d 1 minus 0.42 x by d equals 0.36 250 367.48 1 minus which comes as 93.1 0.13 kilonewton meter. This one in Newton millimeter, and we are getting after the simplification the 93.13 kilonewton meter. Ultimate moment capacity AMU 68.98 kilonewton meter due to steel failure. So, the problem we have done in the very beginning, that is that we took this problem B, I think where is that one, sorry, we anyway we took the problem, we can again write down, there is nothing wrong in it. We have taken the problem, just summarize the whole thing. The 316 bars and effective depth 367 computed, M20 Fe4 on 5, we got MU due to concrete failure equal 93.13 kilonewton meter, and MU due to steel failure (68.98 kilonewton meter). We have taken the section, the overall depth 400. We have taken this section and we have got these two values. Our objective should be that we have to provide the section, the 93.13 kilonewton meter, and the other case we are getting 68.98, almost you can say 25, difference of 25 kilonewton meter. That means we can add one more bar, we can find out, we can check, we can add one more bar and we can find out that whether it is coming closer to 93.13 or the other way also it may exceed also. In that case we have to choose that bar also, that bar, that 16 die, instead of that we can use 12 4 numbers. So, the design is such, where the design comes, that we have to optimize this section. The steel and concrete failure, the moment capacity due to that steel failure and due to concrete, it should come closer, otherwise it is not an optimum design. And that this one we have done, this particular problem we have done, this problem we have taken it as a analysis. Everything is given, we are finding the moment carrying capacity. The other alternative, what you have to do, that you have to do the design. Therefore, you have to do lot of calculation. If you do it with the calculator, then you have to do lot of calculation. Again, you change the depth, not the one process, it is not a single process that you will go and you will solve it and you will get your required depth, not like that. Maybe you have to change the depth, or maybe you have to change the bar diameter. So, the process is little bit, you can say, iterative, and it comes in that fashion. What we shall do in the next class, we shall solve the problem, few more problem we shall solve, and there we shall do the design. we shall summarize our beam problem. Let us summarize it. We call it limit state of we are considering only flexure, only bending we are considering. So far we have taken singly reinforced section and rectangular. Singly reinforced section and rectangular. It is possible this one slab, this is the part of the slab, this is the rib or web of the beam. If you take this part, this is your slab, this is web. We take it, we can also take it as a T beam. Where we shall take the effect of the slab, because when we cast the slab and beam, we cast all together, the same time we cast it. So, we can consider this one as one unit, and when we take this one unit, our code says that how far you can go. That means, this is the beam, whether shall we take that shall we take this portion only? No. Shall we take this portion only, the rectangle, whatever we are considering, then we are not taking the effect of this flange part or the slab part. We can go certain distance from both sides, from the center line of the beam we can go, and we can take the flange width. When we are considering that, when you are taking that part, then we consider it as a T beam. Similarly, it is possible, as I say, at the corner, at the side, at the end, the beam could be like this. That means, the slab ends and the beam, either you can take it as a L beam or inverted L beam, whatever you call, we can take this effect. This is all related to your singly reinforced section, where all the reinforcement in the tensile side. It is also possible that we have to consider the other part, that is called doubly reinforced section. So, one part the singly reinforced, that so far whatever we are doing, we have done so far that rectangular one only. And the other one doubly reinforced section. In this case, we provide reinforcement. This is your tension side, compression side. What is the basic philosophy? The basic philosophy is that tension side you are providing the reinforcement. Concrete can take compression at the top. For this usual case we are talking, concrete can take compression at the top, and from the equilibrium consideration we can provide that you say equivalent your tension reinforcement, so that it will be in equilibrium and we can calculate the moment carrying capacity. In sometimes it may happen due to some problem that we cannot increase the depth. The moment is such that we cannot increase the depth. The moment has come due to computation, due to the load, external load, we have got whatever moment we have got it, but we cannot increase the moment of resistance. That means, we cannot increase the depth. It is always preferable that increase the depth, because if you increase the depth, then it is coming square, d square, whereas if you increase the width, then it is just simply multiplied by b only. So, it is always preferable you increase the depth, that is why you always increase the depth. If we increase the depth, we can get that all section we can make it singly reinforced section, but sometimes it happens that we cannot increase the depth. Therefore, what you have to do, the moment carrying capacity due to singly reinforced section, we can get certain say mu 1, the moment is mu that which we have to provide, mu 1 we have got from singly reinforced section. The remaining balance mu minus mu 1 we shall providing compression steel. So, if you provide the steel in the compression side, similarly you have to provide for equilibrium, we have to provide in the tensile side also, you have to provide the reinforcement. And then we shall get tensile side that something this one for this say AST1, for remaining part say AST2. So, AST1 plus AST2 we have to provide in the tensile side. So, that we shall do it in one class, that we shall do. So, this is the whole thing we shall do. So far the limit state of collapse taking flexure only. There are other parts also that we have to taken care of, shear also we have to taken care of when we shall design the beam. Okay. So, thank you.